Good morning, everybody. My name is Jan van Ootelaar. Indeed, it's a difficult name. And it's also a difficult subject, so I'm going to try to make that as simple as possible. And the first thing that happened when I got the invitation from Jürgen is that my secretary said, why the hell do you need to go to a conference on driving simulators? Because you know nothing about them. And she was right. So I will not address anything on driving simulators today, because that's something that you already get in a lot of different presentations. So what I will do is focus on all the things that are connected to it, and that in the end, when we draw a conclusion, will give us a picture where the outlook should be, where we all together, you as well as we, have to work on to improve the products that we have. So let's go to the first slide. I will give you, in a summary, on one slide, an overview of what we do within the company, because I think it's important to understand the background and how we act. So we are a company, we have 3 product lines focusing on safe and smart mobility, and we basically follow the V-cycle. We base ourselves on research. A lot of it is coming from T&O, a lot of it is coming from other areas. We do software development, we have a lot of virtual environments, we run engineering, and we have a number of validation areas where we have facilities to validate the models that we build, but also to run physical tests. Last but not least, we have a department that is focused on homologations, and we are certified as a technical service to do all kinds of homologation activities. That is what we do. But where we come from is from the safety area. And if we look at ADAS and the way how things have developed, safety remains a very important cornerstone on the ADAS development. And that is important, because we as engineers, and most of us are engineers, when we think about ADAS, we think about technology, and we think we have to resolve it with technology. And that's right, because automation can reduce the largest risk we have. I couldn't find a better picture, but this is a nice lady multitasking in the car, and she has a lot of things to do. She's not even watching the kids, but her telephone. So what is the biggest risk if we look at the way we have set up our systems? In fact, it's the driver. And we try to cover that, and we try to compensate for that with our systems and technology on board. Given that, our vision is that we should end up with the driver, but it also has to start with the driver. So if you look at the 2 axes on which we base our development cycle, and we deliver development tools, and we focus on both the simulation side and the validation side, then clearly we have started on the passive safety side with the driver, because occupant protection was always the key on passive safety. Over the years, that has evolved into integrated technology, where we see that multiple systems in the car are going to have an impact, on the car itself, but also on each other. So we get systems that are interactive and that are difficult to manage. Moving from a number of independent ECUs into the car into a multiple function ECU is something that's happening today. We have seen that on a number of cars, but it means that the complexity as such is increasing. And then we have the third change, which is the world outside the car. Because at the second level, we are dominating our own design, and we are looking at the car, inside the car. But now with the world coming at us with ADAS systems, with cars having sensors, all kinds of sensors that go outside, we suddenly have a world around us. And the world is something that is making our life difficult, because it's not a static world, it's a dynamic world. It is an area where we see phenomena that we have not seen before, and it's an area where we have to work together with multiple companies from different domains to be able to tackle it. So that gives us a challenge that is enormous. We see that back in the way how we set up both the simulation and the validation side. Because where in the past we would do batch computing offline, as you saw in the Adams presentation a little bit earlier, today we run in-car, we run parallel computing, and we slowly move to computing power inside the car. The fact that you have a gearbox inside your car, if it's an automatic one, that's a self-learning one, is a typical thing. So that means that also from an application point of view, we are moving from an offline independent system into a more or less self-learning system. And that's something we have to adapt on the validation side as well. So there we will move very slowly from what we see today, functional testing, towards self-certification. And last but not least, we do think that in the end we will go into deep learning on cars on the validation side. If we do that, that means that we will move to intelligent vehicles. That's the stage we are not there yet. If we can conquer the third phase, including the automated vehicles, then I think we should be well on our way to integrate automation into vehicles. So what we see today, and that's what we will be addressing, is the gap that we have between validation, between simulation, whether we call it testing and simulation, and that gap is increasing as we take the third dimension, the world, into it. It means that we have a huge gap to cover. So that leaves us with a very simple question. The simple question is, how can we bridge the gap between simulation and testing? In fact, Jürgen, when he announced the conference, he said it is, can we bridge the gap between testing and simulation? And I thought, he made a mistake. It is between simulation and testing. Is it true? For my part of the presentation, it is. But at the end, we'll come back to it, because he was right. And I'll show you why. In fact, if we bridge the gap, we need to move from a virtual to a public environment. And how can we bridge between the two? The way to do it is to make sure we have a chain, a development tool that allows you to run in phases and in steps from one side to the other. So through a virtual one, the laboratory setups, a closed track environment to do specific experiments, an open track environment to check your, let's say, natural driving behavior, and last but not least, a full effect study on public roads. And we'll go through each of those with a snapshot. Let's start with the virtual. What is essential in a virtual world is that you have a decent product, and for ADAS type of applications, you need to be able to connect two different items. It is the vehicle itself, with everything that's around it, and it is the world, the outside world, which is complex and that we need to break down. So what we did inside Prescan is that we put it up as a platform, and we have split vehicle model into three. The driver and the vehicle as a central part. We have our sensors, which are located on the car, and which we, from a technical point of view, evaluate. And we have all the logic around it that goes into it. On the other side, if we look at the simulation and we look at the world, we see that it's key to have a proper definition of road and environment, which of course is connected with the sensors. We see the traffic, which of course is connected with the driver. And last but not least, we have all the additional information coming into our system, which is the V2X, and everything which is cloud-based information coming at us at real time. So this looks nice, and we have made a number of models. So for each of the sections, we have our own in-house models. But soon we realized that was by far sufficient to cover the topic. Because there are so many setups of development chains inside OEMs, at tier ones, at different suppliers, that it's crucial to be flexible and to integrate in those chains if needed. So we've set up a number of partnerships which illustrate, I think, the complexity of the subject that we are handling. And those partnerships are set up in such a way that they are able to plug in into the ADAS or the automated simulation. What you see in the middle is that we have different type of companies. We use VI grade, for example, for the driver models. We are able to integrate with TNO on a different type of subjects. But we also connect to most of the map companies that are working on high definition maps, trying to set up, let's say, a static type of environment which is as detailed as possible or as needed for this type of simulation. But that's only one part of the story, because we see that customers use this simulation platform in different settings. One is that you can do an offline evaluation, you can do a lot of offline evaluations, but in the end, if you need an analysis of a continuously changing environment, which is the world around you, you need to have a proper scenario analysis, which you do on a cluster. So some of our customers run massive parallel processing on a cluster, and they do an analysis on X hundred, X thousands of scenarios overnight to see what the effect is on the changes they have made on the vehicle or changes that they have made in the traffic. The second thing that happens is that we connect, of course, to hill, vil, and driver in the loop. So we're not completely unfamiliar with the simulator side. Because here it is clear that you would like to connect your virtual world with the physical world as early as possible in the development. A, to run in parallel and to learn from it, but B, also to optimize the models that you use inside your virtual world. And here you see a number of different settings. We work, for example, with Concurrent very well together on the fact to set up a hill system and to work in a real-time hill environment. We do run the core of pre-scan at real-time speed. We are optimizing the sensors to be able to do the same. And our objective is very clear. We will, in any case, focus on pre-scan as a platform with a very specific, detailed sensor focus and a detailed analysis on the world model that includes real-time performance. That is our final objective. So are we completely unfamiliar with vehicle dynamics? No, because we also have Delft Tire. And most of you know Delft Tire from the vehicle dynamics side. So we think it's an integral part, as a very critical aspect for the total vehicle behavior, is that small piece of contact that we have between the rubber and the road, and that allows us to drive the car. So also there, real-time Delft Tire, connecting with hill and vil, but also as a very serious input for pre-scan. Is this enough? No. Because what you need is an end-to-end simulation tool. So we've seen the world, yes, we connect. We've seen the vehicle, yes, we connect. And we do that through the road. But we also need a human to be in. And the human is essential to make the first part from passive safety to active safety. Our job on the safety side of business is to focus on the human from a safety perspective. So we have developed a body, a dummy, that is fit with muscles. That is, it's possible to activate the muscles and to have a kind of dynamic behavior in the car, so you can move from a proper pre-crash analysis into a crash analysis with the same type of setup. This is essential on the safety side. It does not address every need to have a proper vehicle model, or sorry, for a proper driver model. And we'll come back to that at the end. And then last but not least, our objective on the Delft Tire side, and I just wanted to make sure you clearly understood the message, is that we will focus on all the external conditions that are impacting the behavior of the tire and the modeling of it going forward. So we're working on the temperature model and the things that come along with it to be able to do a proper and a better representation of that. Let's take the second step, the laboratory. This is something we have been doing for quite some years. If I look at an old movie, and I took a movie which is 10 years old. You all have brilliant movies. That's not our objective. Our objective is to have a movie that has a correct representation of the physics, which is not always what you're looking for. So what you see here is on the left side, a simulation where a car comes out and comes in front of a second car that is moving up. And on the right-hand side, you saw the same movie, but in reverse. In fact, the car that is driving is standing still, and the vehicle, the traffic around it is moving in an inverse way. We are operating this as a first check on a system on a car to see if we can, for dangerous situations, look at ADAS type of applications to monitor the behavior and to see how the function of the car performs. We then move normally to closed track. What do we do on closed tracks? Today, very little, because most tracks are not really suited. Because the test tracks that we operate, and that most of the OEMs are at the moment looking at, are tracks that are focused on the vehicle. They focus on durability, they focus on all kinds of mechanical things, but they don't focus necessarily on what is around them. The focus on the vehicle is not sufficient to do a proper assessment on ADAS or automated. What you need for that is the next generation test track. The next generation test tracks is focusing on the sensors. What does a sensor need? How is the environment? Do I need a tunnel with a very, let's say, quick change of light conditions? Do I have reflecting things in my area? What is the traffic doing? How should I look at communication? And last but not least, as soon as we get to connecting cars, the question is, how interoperable are those cars? Because that is a crucial thing. If company A decides that 0.1 of a second is sufficient in an algorithm to react, and a second company decides 0.2 would be sufficient, how can the two of them work together and have a seamless system? So we need to work more in a collaborative mode than ever before to be able to do that. And people are doing it. because we have several tests that are conducted on tracks that we operate, where different companies come together and they check the systems, one to another. It doesn't mean that if it doesn't work, one is better than the other, or one is wrong and the other is right. It means we have to ensure that things work together. And the big question is, how can we make that work? So what we need to do in signing up for new type of test tracks is focusing on the dynamic environment around and including the vehicle. Yeah. And then you get a whole chain. This is a rather complicated picture. We do all the normal stuff. We look at reliability, we look at robustness. We don't just test functionality, we test robustness of the system. We investigate the issues, we collect all the scenarios, which we then use in the virtual world. And last but not least, we improve the models. That is something that is an essential part of our development. The loop back into the model needs to be there. So we need a close collaboration from functional design to the robustness analysis. Now let's take a look at some of those test tracks, because there are currently 3 tracks in the world that have been designed with this in mind. The first one is in the US. It's called M-City. M-City is a small test track close to the University of Michigan, which has been designed solely to test ADAS type of functionality and automated driving. The way how they did it is reverse to what you normally would do. We see in the presentation this morning on VI Grade that we have a number of test tracks inside our models. Here, it was done first in a virtual world. It was an application we as TASS never thought of. But the company that designed this site, designed it inside Prescan, did all the possible scenario analysis and came to the conclusion then that the layout of the site had to be in a certain way. And that's what you see on the left. It's operationable, it's booked 100% of the time today. It's not possible to get any slot. Yeah? So the US is really making moves. The second one is in Sweden. Asta Zero is a big test site near Hellered. They are closely connected to Prescan, and also Asta Zero is backed up with a full view and a full layout in Prescan. And last but not least, this is not a closed test track, but an open test track. It is a motorway with a number of B roads and crossings that we have in front of our office, and that has been completely equipped with sensors to be able to detect all the vehicle and all the traffic which is on this road. I'm going to show you a small movie. It is on Asta Zero because I think it's a good illustration on how simulation and testing are working together and how you could bridge this specific gap. This is a video that was made by Volvo in Sweden. It's by courtesy of them that we may use it. This is the lady that is running the vehicle dynamics group. My Swedish is not so fluent, so I thought I'll just skip that. But what they have done is, they have built the ABS legal requirements inside Prescan. They've changed it to make it more stringent, and they are doing a test in a simulated world where 2 trucks automated, so they're following each other, they have ABS on board, are approaching a target that's in a standstill in front of a crossing. So what you see on the video is that, or on the movie, is that they performed it in a virtual world, went out to the test track and did exactly the same thing. And as you can see, the Swedes are pretty content that it worked out well. So, well done. So, I'm sure it didn't always go wrong or right, but that's exactly where it's meant for. So, but it's fine to have this done. So, that is a good way of doing a specific situation, but it doesn't give you a final answer. Because these are all specific setups, it's defined conditions, and even if you tell somebody, act as you do normally on the road, it's still preset. So you need to have another way of doing it. And that's where we need our open test track for, and how we use it to evaluate things that are different. Because on the open test track, the main idea is, A, to check the performance of your technical systems, which you can do if you have a good view on all the cars around you. This, for example, is a setting where we check sensor readings that work in practice in a laboratory on a closed track. But the question is, how do they react to traffic that is acting very differently? And the second thing we do is that we use this track to see the effect of open traffic on the sensor itself. Because there is a big difference in how cars are being acted, whether they are dirty, whether they are not dirty. The question is how they are set up. We do need different traffic conditions to be able to judge that. And that randomness, the natural driving, is something you will never get on an isolated test track. So this is a phase that we feel is crucial to be able to do that. So then let's move to the last one, which is the public road. And I think there's a lot of truck examples, but they have made a pretty large effort over the last years. I will show you a video on a truck platooning that was conducted last week. It is it's called the truck platooning, European truck platooning. It was a subsidy, and there were 6 OEMs that conducted this test. So it's DAF, MAN, Daimler, Iveco, Scania and Volvo. And they all drove from Vienna to the Netherlands, near Rotterdam, to the port, with fully automated platooning. So they have set up the systems independently, and the 6 times 2, so the 6 teams, came up with this setup. This was a demonstration effort to convince governments that they should be working on it. It was a demonstration effort to check whether this in real traffic would work with a setup like this. And for us it was a good connection, because we have built a demonstrator that consists of 4 different drivers in 4 different platooning type of applications, and where you can connect each driver with one button. You can connect to the platoon or you can disconnect, and you can merge and submerge. So we do think that this technology, and if people are talking about motorways and the first applications are highway applications on a specific lane, then this is definitely one that is out there. You can check it for robustness. Do I need 0.5 seconds headway? Do I need a lot more? Everything you'd like to understand is conducted following this process. Okay, so this brings me to not the end, but almost the final part. Yes, we do need to connect the virtual world with the public road, and we have a number of specific areas that we can use for that. I would assume that whether you use a laboratory in a big or a small sense, that is something that that is normal. But there are still a number of things we have to keep in mind. When we talk about vehicles, and we talk intelligent vehicles, there is a large number of scenarios that will never happen in real time, or are so exceptional that you will never be able to test. How can we safeguard ourselves for that? So we need to go into a situation where we can assess an unlimited number of possible scenarios, specifically the system critical ones that rarely happen, that you need to identify up front. We need to be able to reproduce scenarios in real time. It is very hard to do that. So we have to get a tool to be able to assess it. And we have to be absolutely sure on our ground truth data, because subjective evaluations on the road are difficult to reproduce. And then there is, of course, the safety aspect, that some systems and some scenarios are simply too difficult and too dangerous to test. So how can we assure then that we can test a vehicle, that we can accept that it has a robustness which is high enough according to our standards, without driving the 100 million miles that we see today that people do? So if Google is indicating they have driven 1 million miles on their car, most car companies smile and say, well, I tend to do 5 to 10. But if you ask them, did you get that specific setting on the sun? And are you sure that your camera is working in that condition? Most of them will say, I'll recheck. So it is absolutely critical that we link testing with simulation. So what we need an integrated tool suite where we for sure have a very detailed simulation environment. We need test tracks that can give us the confidence that the systems are functionally correct and that we can collect that and make the connection. And last but not least, we need field tests. We need areas where we can experiment and run those field tests and bring them into a real-life robustness situation. So this is what we do. And with this, we see that this is what we call a methodology for safe autonomous driving. And that brings me back to my secretary. Because she was right. And also Jürgen was right. Because I have not mentioned the word simulator in a lot of slides. It was only on one slide. And that was correct, but that is not the future. Because if you look at all this setup and all the system that you saw, then it's focused on the vehicle, it's focused on the system, it's focused on the world around it. But it leaves the driver outside the scope. So if we get to the point where we can implement this, our next step will have to be that we take the driver into account and that we create a simulation environment which is so natural that all the aspects that we see, that we can work on that in a virtual world before we go out to the road. So once we close the loop on safety, the next step is close the loop on the driver. And that is the reason why my secretary asked the question. And I still think it was right to be here and to present to you from simulation to testing. But your conference is from testing to simulation, which is the next step. And that is a perfect one. Thank you very much.